Good morning, everybody, and welcome to this quick recording for this session that is dedicated to homework sets 4 and 5 and 6. I'm going to have a brief discussion of this homework. I know we did some of this discussion before in lecture, but probably it was not in-depth enough for some of you. So you requested a little bit more analysis of these problems. So I'm going to share those problems with you. You are required to submit 2 problems of each set. So you don't have to submit the entire list. So let me share with you my notes in here. So this is homework set number 4. So this is homework 4. And homework 4 has about 5 problems. You're required only to submit 2 of this. So in the first one, it tells you that you have 4.6 times 10 to the power 20. Okay, I need my drawing pen. So it's 4.6 times 10 to the power 20 kilogram of carbon dioxide. So basically, this is how much you have. We know carbon dioxide is made up of carbon, which is 12 molar masses, plus oxygen, which is, but you have 2 oxygen in here. Each and every one of them comes with 16 molar masses. So the total molar mass for carbon dioxide is 44 grams per mole. Okay. Now, the key question in here is that out of this, of course, we're going to extract the oxygen. And the oxygen in this represents 32 out of 44, because you have 2 times 16, which is 32, and 44 is the entire molar mass of oxygen. Obviously, the entire mass of oxygen that we're going to extract from this carbon dioxide is going to be this much. Okay. So this is going to be in kilogram, because this is how much oxygen you will have in kilogram. Now, you take this oxygen and you combine it with hydrogen, and all of a sudden you form water. And water is H2O, which is made up of 2 hydrogen atoms, and each one of them has a molar mass of 1 gram per mole. And oxygen is only 1 oxygen, and it is 16 grams per mole, for a total of 2 times 1 plus 16, which is 18 grams per mole. Now, this amount of oxygen will combine with enough hydrogen to form water, and that means that the water that you're going to end up with is 18/16 of this much, because remember, 16 grams out of 18 is oxygen, but your goal now is to form water, not oxygen. So 18/16 times the amount that you start with, which is 32 divided by 44. Don't forget that this has to be multiplied by 4.6 times 10 to the power 20 kilograms. So if you do the math, you will end up with enough water that is about 3.7 times 10 to the power 20. All you have to do is just do this multiplication. Don't forget the 4.6 kilograms. So this is how much water you're going to end up with. And it says in the question to compare this number to that of the oxygen, that of the water on Earth oceans, and the Earth ocean is 1.4 times 10 to the power 21. So it's 1.4 times 10 to the power 21. This is how much water is. This is Venus, how much you can make on Venus. This is how much water is on Earth. Okay, so if you take all of the carbon dioxide and convert it into water, this is basically what you're going to end up with. So this is cancels with this. I'm left with 1. So at the end, it's 3.7 divided by 14, and the ratio is, let me fill up the calculator quickly in here. So 3.7 times divided by 14. Again, you need to probably do a little bit more of this analysis on your own. Mainly, at least the numbers, carrying the numbers, but the comparison should be about 26% of water on Venus that you could gather than how much it is on Earth. Okay, so all you have to do is just I multiplied by 100 to get the percentage, of course. Otherwise, you're going to be 0.26. So this is question 1. Question 2 from your answer to problem 11, how deep an ocean would this water produce if it were the same depth everywhere on the surface of the Earth? Obviously, this many kilograms, so this is 11, so that's the first problem. Which number is that? That's problem 11, yes. Problem 12, so I'm running out of room, so I'm going to erase. I'm just going to keep the last number in here because we need it. So I'm going to go back into my drawing tool in here and erase everything in here. Hopefully you guys have had a chance to go through this. as I said, I wanted to really have this recording short. So delete that, because there are so many problems that need to be. So at the end, this is how much water really we ended up with from Venus, 3.7 from the previous problem, times 10 to the power 20 kilograms, okay? So that's how much water you could end up with on Venus, okay? If you take all of the carbon dioxide and convert it into water by having enough hydrogen to combine with it. Now, what is the depth of the ocean? You need to know from this part that the radius of Venus is 6,050 kilometers. If you convert it to meters, that's 6.05 times 10 to the power 6 meters, because you have 1,000 meters in a kilometer, but you have another 1,000 in here to put the decimal point. So this is how much the radius of Venus is. The area of Venus, the surface area of Venus, of any sphere for that matter, is 4 pi times the radius squared. And the radius in this case is 6.05 times 10 to the power 6, the whole thing squared. So this is the area of Venus, basically. You take all of these numbers. So if I'm doing this number correctly, so let me do this again. 4 times pi, I'm doing it on my calculator, by the way, times 6.05, and I square this number. So it's going to be 3.6 times 10 to the power, am I missing pi squared? Yeah, that's correct. So 3.6 times 10 to the power 13, basically. Okay, so just do the numbers in here. Because 6 squared is about 3.6. I mean, it's 36. So we take the decimal points, it's going to be 3.6. And don't forget, when you power the square, the 10 to the power 6 becomes 10 to the power 12. Okay. So this should give me the surface area of Venus. Now I have this much water on the surface of Venus. I know 1,000 kilograms. That's another thing that you need to know. To know also is about cubic meter in size. So the density of water is needed. This is a known fact that the density of water is for every cubic meter you have 1,000 kilograms. But this is how much water you have. So really the volume of water that you will end up with is going to be 3.7 times 10 to the power 20 divided by 1,000. Which means that this is 3.7 times 10 to the power 17 cubic meters. That's the volume. Okay, this is the volume. Take the entire surface and fill it with water, and you're going to see how much the depth of the water, which is this in here. So this is the depth of the water, is going to be the entire volume, which is 3.7 times 10 to the power 17 cubic meter, divided by this number at the end of the day. That should give me the answer in here quickly. So let me try to see if I can get the numbers quickly in here. So we said 3.7 times 10 to, oh man, I should not have multiplied. Okay. I'm going to leave it to you guys to finish this calculation. So don't forget that the surface area is what you had from before. That should give you a depth of less than a kilometer. It's going to be about 800 meters, actually. Okay, so this is problem 12. So let me get my tools again in here to erase stuff in here so that you guys, please make sure you go through this and pause the video if you want to, okay? This is this one in here. Problem 13, it says Kepler's third law from the unit 12 describes planetary orbital sizes relative to Earth to orbit, which is 1 astronomical unit. One method to doing this is to use radar arranging between planets. Basically, you send the radar to Venus and it bounces back. You're going to take the time it takes. So here is the analysis. Basically, you have Venus in here. and to drop. So you have Venus in here, you have Earth in here. You send a radar hits Venus and bounces back. The entire time it takes, according to this problem, is 276 seconds. Okay, we know how much light travels in 1 second. Light speed is 300,000 kilometers per second. So you can find the distance the light has traveled. The distance is back and forth. Okay, so we want half of that distance to just give us the distance between Earth and Venus. So it's going to be half this number, which is speed times the time. And the speed is 300,000 kilometers times 276. And it's going to give me a number in kilometers. So let me quickly do it. Don't forget to divide it by 2 because you're going to have half that because the laser beam goes and comes back. And we want just the time it goes, which is half that time. So is going to be 276 times 300. Oh man, I should not do this. Can I enter in here and see? I'm still doing the same mistake as before. Okay, I need to start a fresh calculation. Times 300,000 and divide that by 2. So it's going to be 41,400,000 kilometers. 400,000 kilometers. That's basically according to this calculation. So it's just this distance between the Earth and Venus on its closest approach. Remember, the problem says that the Earth is from the Sun 1 astronomical unit, and Venus is from the Sun as 0.723 astronomical units. So this distance is actually going to be 1 minus this number. So 1 minus 0.723, so it's going to be 0.2 something in here. 1 minus 0.723 is 0.277. So this is 0.277. So this number in here is 0.277 astronomical units. So if I want to know how many astronomical units are, how many kilometers in astronomical units, so 1 AU should be 41,400,000 divided by 0.277. That's going to be a number, of course the 2 is part of the other one, that is around 150 million kilometers. It's going to be slightly less if you do the calculations in here. That's what we know about the AU. AU is about, so I'm not saying equal, okay? So this is about, you need the exact number. You need to compute the exact number. That's the whole problem, that the whole exercise of this one in here. So again, this is basically the analysis. If you guys need more help or more time on this, please, you can pause the video, or you can again reach out to me if you need more help with this problem. Venus and Earth make their closest approach to each other during the inferior conjunction, that's from the unit 11, every 583.9 days. Use a diagram to show that. Okay, what you need to know about this problem in here is that the Venus period around its axis is 117 days. Okay, so it's 117 days, and if you take 117 days and you multiply it by what, 5, you're going to get almost the exact same number. So let me do this. 117 times 5 is 585. So 585 days, Venus would have spun on its axis 5 times, okay? 5 days, basically, 5 Venus days. And of course, noon to noon is a day on Venus, and it takes this much day. But remember, Venus is moving retrograde. It's not moving in the, it's not moving while it's spinning. So as it's going like this, it's spinning and going in that direction. So if the Venus and the Earth were facing each other one day, and after 583.5 days, they will also be at their near-Earth approach. Practically, they will be facing each other at the same time, because this is a ratio of 5 to 1. So this is basically what the problem is saying. You can draw it and draw 5 times basically Venus, and you're going to see that every 5 times they're the same size to Venus, and every 5 times is going to face the same side to Earth as it comes back to their nearest approach. Okay, you can do the diagram, and that's going to be fine too. If you have, again, questions about this homework problems, please reach out, okay? So this is easy enough, actually. It's just the ratio of 585 or 583 to be more specific. 583.5 divided by 117 is going to be 4.999 something. So practically it's 5. That's why they're multiplied by 5. Each Earth covers about 1 degree per year, and that is because Earth takes about 365 days to go around the sun, whereas the circle has 360 days. So 365 and 360 are very close from each other. That's why the Earth is 365 per year, and the circle is 360 degrees. So this is roughly about 1 degree per day. That's how much the Earth goes around the sun. And the solar day is basically, remember the sidereal day here is a little less than the actual, the noon to noon day, which is the day that we measure. But if the Earth were going to go retrograde, then in this case, here is the deal. The Earth spins around its axis and moves around the sun. So if it spins exactly a full cycle, it's not facing the sun. It needs to spin a little more to face the sun. So this is the difference between the sidereal day and the solar day. And what we want to know, if the Earth was spinning in the opposite direction, obviously it's going to reach this point. It's going to reach the point where it's noon already before it completes a full cycle. So in other words, the solar day will be shorter than the lunar day. And you can actually compute it too if you want to. But the point in here is that you have to understand when the Earth goes retrograde, it's going to be noon before it completes a full cycle. So basically, it's going to be less than 23 hours and 56 minutes. Okay, so this is homework set number 4. Let me go into homework set number 5. Homework set number 5, the first one says, calculate the how long it takes light to travel 150 million kilometers, which is an astronomical unit. Remember, the time is the distance over speed, and the distance in this case is 150 million kilometers, and the light travels in 300,000 kilometers per second. So this is the distance, 150 million. This is kilometers per second. If you take this and cancel it with that, so I'm going to be left with this one in here. So it's going to be 115 divided by 3 is by the way 5. So 50, and then I have another 0 in here. So it's about 500 seconds. 500 seconds, you can divide it by 60 again to find how much that time is. So it's 500 seconds, but I want it in minutes. So 60 seconds per minute. So this cancels the second with the second, of course, the 0 with the 0 also. So it's going to be 50 over 6, and 50 over 6 is what? About 8 times 6 is 48. So it's a little over 8 minutes. And that's what we know about light, okay, a little over 8 minutes. So 50 over 60, 50 over 6, I'm sorry, is about 8 and a third of a minute, okay? 8 minutes in 2 seconds. No, 8 minutes. Yeah. In 2 seconds. Okay, again, you probably need to, no, actually, this is close enough, okay? Yeah, this is close enough for this problem. Actually, this is the exact answer, okay? Anyway, so this is problem 11. Problem, let me erase this thing here. Again, if you want to, you could pause the video. It's just distance over time. Distance over speed, I'm sorry. How much brighter does the sun appear from Earth when their separation? How much brighter does the sun appear from Earth when their separation is the smallest, 0.983 astronomical units, compared to when they are at their largest separation, 1.17 astronomical units. We're going to compare two positions. Remember, the path of the Earth around the sun is not exactly circular, but rather it's elliptical. So at some point, the Earth is close from the sun, and at some point, the Earth is far away from the sun. So this is June 21st. And this is August. I mean, this is, what's the opposite? Sorry. This is January, actually, or December 21st. And this is June 21st. So the distance in here is slightly less than an astronomical unit. And the distance in here is slightly more than an astronomical units. And that is basically in a nutshell what's going on with the Earth. So we want to see how bright the sun is, relatively speaking, when it's further away compared to when it's closer away, when it's closer from us. Obviously, when it's closer, it's brighter than when it's far away. So when it's closer, the brightness depends on the luminosity. So I'm going to use the letter L for the luminosity, divided by the distance squared, which is the the area, which is in this case 4 pi r squared. And r in this case is the distance. So I'm going to call this one in December, the distance, the smallest distance, I'm going to call it D1. The further distance, I'm going to just call it D2. And that is what the radius is. So the sun emits light, and this light is going to go through an entire sphere, not circle. Okay. Okay. So now I need to take this number and basically, yeah, and compare the luminosity, it's the brightness. So this is the brightness. When it's close, is going to be the entire luminosity. So that 10 to the power 26. We really don't need that number for this particular problem. Divided by the distance, and the distance I'm going to call it D1. So this is in December, and in June is going to be 4 pi D2 squared. So if I take the ratio of these two, I'm going to find luminosity over 4 pi divided by the distance squared divided by L over 4 pi divided by the distance squared. Everything cancels actually, and the ratio flips because you're dividing by a fraction over a fraction. So at the end, the ratio is going to be just D2 squared over D1 squared, which is just 1.017 over 0.983, the whole thing squared. So if I do this quickly in a calculator, so I have 1.017 divided by, is this correct? Yeah, divided by 0.983, 0.983, and because this is actually depends on the square, so I really have to square this number. So it's going to be 1.07. That's the ratio. It's 1.07. That's the ratio of the brightness. In other words, the sun is 7% brighter in this December because it's closer than in June, which is because the sun is further away. Okay, that's basically in a nutshell. So let me again, if you guys need help or if you think that this is not clear enough, please let me know so that we can have a one-to-one session and go a little bit more in depth about these things in here. Okay, I need to do this one more time. Okay, so, excuse me. 13, how much, the sun is about 10 billion times brighter than the next brighter star, which is Sirius, as seen from the Earth. How far would we have to be from the sun for the sun to be as bright as Sirius? Okay, Right now, the distance is 1 astronomical units between us and the sun. So here is the sun, here is the earth, and the sun, of course, is super bright. But Ceres is about 1 billion times less than 10 billion. So billion is 10 to the power 9 times 10 is 10 to the power 10 less than. So we need to move far away from the sun to a certain distance so that the dimness drops by that factor, by 10 to the power 10, less than what it is today. So right now the distance is 1 astronomical unit, and again, according to that analysis, the brightness is the luminosity over 4 pi times the distance squared. We know today it's brighter than at that distance. And the brightness now is just that luminosity divided by 4 pi times the distance. I'm going to use the astronomical units, so the answer is going to be in the astronomical units squared. It's much easier to do it this way. So if I take this ratio and require it to be about 1 billion times, so L over 4 pi times the distance divided by 4 pi, divided by the luminosity divided by 4 pi times 1 squared, this is 1 billionth less than what it is today. This is 1 over 10 to the power 10. So again, luminosity and the 4 pi cancel, and that should give me, and even the 1 is 1. So that should give me the distance is going to be 1 over distance squared, should be 1 over 10 to the power 10, or cancel everything, so that d squared must be 10 to the power 10 astronomical units squared, of course. So I'm going to take the square root of everything, and that's going to give me the distance is about 10 to the power 5, because when you take the square root of a power, you just divide that power by 2. So in this case, it's 10 to the power 5 astronomical units, or 100,000 astronomical units, 100,000 times further away from where it is right now. This is far more than what the size of the solar system is. This is actually about about 1/10 distance from here to the nearest star. They're not even on Proxima Centauri. You are 1/10 of that distance, and the sun becomes as bright as Ceres in that case, which is the brightest star in the sky. Which means that if you are, or actually there are people on planet near Proxima Centauri, and they're looking at the sun, they will see it less bright than even Ceres. But Ceres is much brighter than us. Okay. So again, this has to do with the luminosity. Okay, and let me go in here to this tool and erase everything, delete. Suppose there is an atom with with 3 excited states. So it has a ground state and it has 3 excited states. Let me go back into my drawing pen here. The background is black. I have to use this pen here. Anyway, it says in here that you have, suppose there is an atom within the 3 excited states with energies 10 to the negative 19, 3 times 10 to the negative 19, and 7 times 10 to the negative 19. You really don't need these numbers for this particular problem, but there is another problem that is coming in the book that I did not assign that requires these numbers, okay? But we're not going to read. All we need is just the fact that we have 3 different energy levels. If an electron began in the highest energy level, determine all the three ways the electron could descend to the ground state. So here is the ground state. Here, and that is 10 to the negative 19 joules, or about electron volts. And this is 3 times that much. And this is the first excited state, and in here, this is the second excited state, which is 7 times 10 to the negative 19 joules. Okay. Oh, all of them are excited. I'm sorry. This is also level 1, 2, and 3, and the ground state is somewhere here. These are all three excited states. And we want to see the different way for it to come back to the ground state. Of course, one way is going from level 3 down to ground state. So that's option 1, from 3 to the ground state. So this is one transition. So that's one photon emitted, okay, of light, and the energy, you can find it in here. Obviously, we're not asked to find the energy for this part. The second option is to go from level 3 down to 2, and from 2 to the ground state. Or from 2 to 1, and I'm sorry, 2 to 1. Can I delete this in here? Selection to delete this one. Yeah, I didn't mean to do that. Here is what I meant to do. Okay, so in here you have from 3 to 2, and you have two options in here: 2 to 1 ground state, or 2 to 1, and then to the ground state. So obviously this one will involve 2 photons, one from here and the second from here, and the other one will involve 3 photons. The third path in here is to go from 3 to 1, and of course from 1 to 2, to the ground state. So again, from 3 to 1, and that only involves another transition from 1 to the ground state. So in this case, we only have 2 photons. So this is the entire discussion for this problem, okay? For the next problem that is not assigned, you're supposed to calculate the energies and the frequencies of these transitions, okay? But that's not assigned, so you're not required to do that in this problem. The only thing in here is just to list the 3 different ways that it can descend, and those are the 3 different ways. A typical frequency used for cell phone communications, I think we did this exact same problem in the homework assignment, in the lecture actually, but if you want to, we're going to do this one again. So a typical frequency used for cell phone communications is 800 megahertz. What is the wavelength of the frequency? How does the wavelength compare to the size of a standard phone? Well, in this case, we have 800 megahertz, and we want to find the wavelength lambda. Remember, the dispersion law says the speed of light is lambda times the frequency. From here, we're going to find the wavelength. Lambda is going to be the speed divided by the frequency. I know the book uses the Greek letter nu, so I better use the Greek letter nu. So the frequency in here is used nu in the book, so that to be consistent. Okay, the speed of light is 300,000 kilometers per second, and the frequency that is given to us is 800 megahertz. Mega is 10 to the power 6. So obviously 10 to the power 6 and 10 to the power 5 cancel. And this is kilometers, so I have to convert it to meters, okay? 300,000 kilometers, so I have to convert it to meters. So I'm left with 1 in here, and there is 1, 2, and 3, and they all cancel the other 3 conversion coming to meters. So it's going to be 3/8 of a meter. That's the wavelength. 3/8 of a meter. That's a long thing. So how many centimeters is that? I have to multiply by 100, and that's going to give me 3/8 of a meter, which is 37.5 centimeters. That's a long way. So it's 37.5 centimeters. So again, the answer is in meters. All I did is convert it to meters in here. So it asks you to compare it to the size of a cell phone. Well, this is probably a big, bulky, old cell phone in here, okay? Or at least a phone that is in the old days, because 37 centimeters has to wrap itself several times the antenna in order to achieve it. And granted that they use half that distance for the antenna, because it's a dipole antenna most of the times. So it's still 16 centimeters, 18 centimeters is a long way. So this is basically for 800 megahertz. But I think the problem we did in the lecture now, I remember, it's 5 gigahertz. 5 gigahertz will give you a much, much shorter antenna than this one, because the frequency 5 gigahertz is 10 to the power 5 times 10 to the power 9. So that takes care of another power and reduces the size of the antenna. Okay, so let me get into the, I really don't need to erase because I'm in the bottom. So now here I'm going to keep it. I don't have to erase that. A hydrogen atom has a diameter of 0.1 nanometers, a tenth of a nanometer, which is called the angstrom actually. What is the frequency and energy of a photon that has a wavelength equal to the diameter of the hydrogen atom? So, okay, so we have the wavelength then is the tenth of a nanometer. The wavelength is 0.1 times 10 to the negative 9 meters, because again, nano is 10 to the negative 9. So this is 10 to the negative 10 meters. That's the wavelength. And they want to know the energy and the wavelength. So the energy is, first of all, the frequency. Did they ask about the frequency? Yeah, the frequency and energy. Okay, so the frequency again is given by the same relationship, which is c over lambda. Now we have lambda, we should be able to find that. Remember, the speed has to be in meters, so it's 300 million meters per second. Divided by lambda, lambda is 10 to the negative 19, negative 10. So this is 10 to the power 18. This is actually a very, very, very energetic wavelength, okay? This is X-rays, hertz. Oh man, it's not 3 times, it's not 10, I'm sorry, I made a mistake in here. So this is not correct. $300 million. 33. Yeah, that's correct. 300 million. Million is 10 to the power. That's correct. That's correct. Everything is correct. I'm sorry. Yeah, you know, when you're trying to rush things and sometimes you don't think about them. So this is 10 to the power 18 hertz. That's correct. Okay. So that's a frequency. The energy then, E of this wave, remember it's equal to H times the frequency. And the frequency in this case, H is a constant 6.636 times 10 to the negative 34 times 3 times 10 to the power 18. And it's going to be in joules, by the way. Okay. The energy is in joules. So again, 18, not 8. 18 and 34 is negative, what, 16? So it's going to be a very, very small energy, but that's, remember, we're dealing with small objects anyway. So 3 times 6.36, 19, or 1.9 times 10 to the power 10. So it's 19.08. Please double check the numbers in here. Times 10 to the negative 16 joules. Again, I'm going to move the decimal point one step in here and add 1 to it. So negative 16 plus 1 is negative 15. So it's going to be 1.9068 times 10 to the negative 15 joules. It's a lot of energy, honestly. It sounds too tiny, but in electron volts, this is a lot. This is about 10,000 times 10,000 electron volts. That's a typical unit that is used for atomic masses and atomic energies and things like that. Suppose the energy of the electron is in its atomic orbital is 10 to the negative 18 joules above the ground state. What wavelength of light would have the photon matching this energy difference? Which band of the electromagnetic radiation is this in? So let's find 10 to the negative 18 joules, first of all. What is that in terms of frequency? So again, the energy is given to be 10 to the negative 18 joules. And remember, the energy is H times the frequency. From here, we can find the frequency to be simply equal to the energy divided by Planck's constant. And that gives me 10 to the negative 18 divided by the energy, the Planck's constant, which is 6.36 times 10 to the negative 34. It's going to be a big number, by the way. Okay. Because frequencies are usually high for this kind of problems. So 10 to the negative 18 and 10 to the negative 34. When I take 10 to the negative 34, it's going to be 10 to the positive 34. So negative 34 and positive 30, negative 18 and positive 34 is going to be what, 16? But don't forget you have a denominator in here. So 1 over 6.636. Am I doing this right? I don't know. 0.15. I think that's the unit. Yes. Okay. 0.15 times 10 to the power 16. That's hertz. But again, I'm going to move the decimal point one way, so I'm going to subtract 1 now. So it's going to be 1.5 10 to the power 15 hertz. Okay. And they want to know, the question actually was not asking about the frequency, it was asking about the wavelength. So we need to find the wavelength using the dispersion law. So the wavelength in this case, lambda, is c over nu, and c is 3 times 10 to the power 8 meters per second, divided by the frequency in this case, which is 1.5 times 10 to the power 15 hertz, which is 1 over seconds, by the way, the hertz. So again, 10 to the power 15 and 8. So when I take 8 minus 15, because I have to take 15 to the other side, it's going to be 3 over 1.5, which is 5. That's easy. Times 10 to the negative 7 meters. Okay, that's 500 nanometers. Okay, that's easy to remember because 10 to the negative 7 is 10 to the is a hundredth of a nanometer. So you have to multiply by 100 nanometers. And this is actually the green light. So it's a visible region. That's the question. So you really don't need specifically what color it is. So it's in the visible range in terms of the spectrum. Okay. You can see it. That's what that means. So which band of electromagnetic radiation is this? It's in the visible region. What is the energy in joules of an extremely powerful gamma ray with a wavelength 10 to the negative 7 nanometer? Again, we need to find the energy. Before we find the energy, we need to find the frequency. Since lambda is given to us, we're doing the last one in here. Lambda is 10 to the negative 7 nanometers. And nanometer is 10 to the negative 9 already. So this is 10 to the negative 16 meters, very short wavelength. We need to find the frequency frequency nu by dividing the speed divided by lambda. We did this several times, so hopefully you guys have this one memorized. So it's 300,000 kilometers or 300 million meters per second divided by the wavelength, which is 10 to the negative 16. When I take 10 to the negative 16, it's going to be 10 to the positive 16 in the numerator. 16 plus 8, that's 24. So this is 3 times 10 to the power 24 hertz. This is gamma rays. You're talking about extreme high frequencies. But they don't ask about the frequency. They want the energy. So how much the energy of this very powerful wave energy. So it's going to be E. Remember, it's Planck's constant, H times nu, and H is 6.636 times 10 to the negative 34 times this 3 times 10 to the power 24. Negative 34 plus 24, that's negative 10. 3 times 6.36, that's something that is, let's find it quickly in here. 3 times 6.636, that's 19.9. Was it 19.9 earlier? So I think I made a mistake. I gave you the wrong number here. So you guys need to check. Anyway, check. According to the calculator, I think I reported the wrong number in there. Okay. Okay, again, it's 19.9, which is 2 times 10, which is 20 actually. So I wrote it 19.9, I approximated to 20. Okay, that's why I wrote it 2 times 10. 10 in here, so that's 1 minus 10. 10 is 10 to the negative 9. So it's 10 to the negative 9 times 2. It's 2 times 10 to the negative 9 joules. I mean, it sounds like it's a small amount, but it's a very, very, very energetic, because remember, usually you write it in electron volts, for this kind of problems, because we're dealing with atomic masses and things like that and small matter, and they become extremely energetic. As a matter of fact, this is 10 to the power 10 electron volts, or 10 giga electron volts. It's a tremendous amount of energy for a gamma ray. Okay, these are all of the problems that you guys have. Oh no, we still have another question. How many of these gamma ray photons would add up to the same amount of energy as a housefly in flight, which has a kinetic energy of about 1 millionth of a joule? Okay, so a housefly, yeah, it sounds like, but that's its kinetic energy. Remember, this is just one of them in there. So it's a housefly. It has 10 to the negative 6 joules. So this is housefly. Basically moving, that's its energy joules. Divide that by the energy that a single photon gamma ray has, in this case, in joules. So it's going to be 1/2 times 10 to the power. Again, when I move 10 to the power negative 6, it's going to, negative 9 is going to be 10 to the power positive 9. Negative 6 plus 9, that's 10 to the power 3. Because negative 6 plus 9 is 3. So 1,000 divided by 2, that's 500 of this will add up to a housefly, basically 500 gamma rays. Okay, so all of these problems are in here discussed. So hopefully you guys have them. Again, you're supposed to submit only 2 of each, not all of them. Thank you. I think this recording went a little longer than what I really planned to be, but hopefully it's clear enough. If not, you can always reach out to me, and we can have a meeting and discuss these things. Thank you, guys.